Welcome to Module 12. In the previous module, we explored some of the theoretical underpinnings of calculus, including the development of the definite integral. Now we'll turn our attention to applications. Let's start with a practical example where we find the area under a curve and dive into its interpretation. Imagine you're tasked with managing the network for a popular online video game. Your challenge is to ensure smooth gameplay across the globe, which requires a deep understanding of the data transfer dynamics as player counts fluctuate. The game server records a rhythm of player activity. As players log in, battle, and log off, the amount of data transferred between the server and players changes. This creates a pattern we can visualize on a graph. The following graph depicts, for a given day, the amount in megabytes of data transferred over time, where x is the number of hours since midnight. In general, when we find the area under the curve, we are finding the cumulative amount of the quantity measured by the function. In this case, the area under the curve represents the cumulative amount of data within a given range of hours. For example, the cumulative amount of data transmitted between 6 a.m., corresponding to x equals 6, and 9 a.m., which corresponds to x equals 9, is found to be 507.98 megabytes. The function that represents the amount of data transmitted is f of x equals 0.06 x cubed minus x squared plus 200. We can see that gaming increases significantly after school hours. Find the cumulative amount of data transmitted between 3 o'clock p.m., corresponding to x equals 15, and midnight, corresponding to x equals 24. The cumulative amount of data transmitted is given by the definite integral of f of x, from x equals 15 to x equals 24. Now we need an antiderivative of 0.06 x cubed minus x squared plus 200. We find this to be capital F of x equals 0.015 x to the fourth minus 1/3 x cubed plus 200x. So the definite integral from 15 to 24 of 0.06 x cubed minus x squared plus 200 is equal to capital F of 24 minus capital F of 15. Now this equals 5,168.64 minus 2634.375, which gives us 2,534.265 megabytes. If we have a function that stays above the x-axis, then the definite integral calculates the area under the function, which represents the total amount of accumulation of the function over an interval. Sometimes, though, we have functions that exhibit both positive and negative values over an interval. When this happens, the definite integral computes a value that represents the net difference between when the function is positive and when the function is negative. If the function is always positive, that is, above the x-axis, the integral computes a positive value that represents the area under the curve. If the function is always negative, that is, below the x-axis, the integral computes a negative value. This negative number is the opposite of the area that lies above the curve. If the function is sometimes positive and sometimes negative, the integral computes the net difference. That is, if the area above the x-axis is greater than the area below it, we will get a positive value. If the area below the x-axis is greater than the area above it, we will get a negative value. And if the area above and below the x-axis is the same, we will get a value of 0, indicating a net difference of 0. Let's look at an example. In the field of artificial intelligence, neural networks are trained on massive datasets. The performance of the network can fluctuate due to various factors, such as adjustments in biases or quality of the training data. The function f of x equals 4 sine x minus 2 cosine x plus 0.5x represents the deviation in performance of a neural network from a baseline, where x represents the progression of training in cycles. Between the third and sixth training cycles, is the net performance over the baseline positive or negative? What does this indicate about the neural network over this interval? The net performance over the interval from the third to the sixth training cycles is given by the definite integral from 3 to 6 of 4 sine x minus 2 times cosine x plus 0.5x dx. Now I'm going to use a little bit of new notation here. but I'm not really changing the process. What we know is that we need to find an antiderivative, so I'm just going to go ahead and start writing that down. The antiderivative here will be negative 4 cosine x. Let's see here, we would get negative 2 sine x. And here, let me see, I need to add 1 to the exponent and get the same number downstairs. So that's 0.5 x squared over 2. And I'm going to put some brackets around all of this. And then a line over here with a 6 on the top and a 3 on the bottom. Now all this is doing is this is just saying I need to plug 6 into this expression, and I need to subtract and then plug 3 into this expression and see what the result is. So this is our new notation right here. So let's go ahead and do that. We see that what we're going to get here is negative 4 times cosine of 6 minus 2 times sine of 6 plus 0.5 times 6 squared over 2. And we need to subtract, and now we're going to plug 3 into this expression. So we get negative 4 times cosine of 3 minus 2 times sine of 3 plus 0.5 times 3 squared over 2. And now this is easy enough to put into our calculator. And when we do this, we find that this is approximately equal to negative 0.21. And so we can see that this neural network over the interval from the 3rd to the 6th training cycles is performing below the baseline. What is the net performance of the neural network over the first 10 training cycles? The net performance of the neural network over the first 10 training cycles is given by the definite integral from 0 to 10 of our function. Now we've already got the antiderivative from part A, so all we need to do here is evaluate that antiderivative from 10 down to 0. So that gives us negative 4 times cosine of 10 minus 2 times sine of 10 plus 0.5 times 10 squared over 2. And now we're going to subtract here, and now we will plug 0 into this. Now I think we can do some simplification here while we do this. When we plug a 0 into negative 4 cosine of x, now cosine of 0 is just 1, so that gives us negative 4. When we plug 0 into sine of x, sine of 0 is 0, and so this is just going to be 0. And when we plug 0 into x squared here, this term will also be 0. And so all we get here is just negative 4 from plugging 0 into this expression. And that means that we have negative 4 times cosine of 10 minus 2 times sine of 10. Now let's think about this one too. 10 squared is 100. 100 times 0.5 is 50. And when we divide that by 2, we get 25. And then we're going to subtract a negative 4, which is going to be 25 plus 4, or 29. And so now when we plug this into the calculator, we find that this is approximately equal to 33.44. The net performance of the neural network over the first 10 training cycles is above the baseline at 33.44. Now there are many instances in which a definite integral may represent a comparison of one process over another. Let's look at an example. 2 power management schemes are available for a notebook computer. The standard scheme represents a typical battery discharge rate without any special power-saving mechanisms. An optimized scheme includes optimizations, such as adaptive brightness or limiting background processes. The percentage of remaining battery life after t hours for each scheme is as follows. For the standard scheme, we have f of t equals 100 minus 5t. For the optimized scheme, we have g of t equals 0.0625t squared minus 5t plus 100. The area between these curves provides a measure of how much battery life is conserved by using the optimized scheme. This bounded area can be found by computing the area corresponding to the optimized scheme and then subtracting the area corresponding to the standard scheme. Mathematically, this is the difference between the integral from 0 to 40 of g of t and the integral from 0 to 20 of f of t. Now we find the integral from 0 to 40 of g of t to be 1333.33, and the integral from 0 to 20 of f of t is 1000. So the measure of how much battery life is conserved by using the optimized scheme is 1333.33 minus 1000, which is 333.33 units. Now we're close to bringing Module 12 to a conclusion, but before we do, let's delve into one more application of definite integrals. The average value of a function over a specific interval gives us insight into the typical behavior of the function within that interval. The average value of f of x over an interval from a to b is given by f average equals 1 over b minus a times the definite integral from a to b of f of x dx. Let's look at an example. Suppose that an online platform uses a dynamic algorithm to place ads based on user activity, maximizing visibility and interaction. In a 15-minute test of the algorithm's performance, the number of interactions per minute follows the function a of t equals 3 times sine of t minus 0.08 t squared plus 17, where t is time in minutes. We want to determine the average number of interactions over the 15-minute period. The average value of a of t over the interval from 0 to 15 is 1 over 15 minus 0 times the definite integral from 0 to 15 of 3 sine t minus 0.08 t squared plus 17. Now, we find an antiderivative of a of t to be capital F of t equals negative 3 times cosine t minus 0.08 over 3 t cubed plus 17t. So the average value is 1 over 15 times capital F of 15 minus capital F of 0. This gives us 1 over 15 times 167.279 minus a negative 3, which is approximately 11.35 interactions. As the course comes to a close, I want to thank you for your active engagement and dedication this semester. The world is filled with all kinds of problems, and with the tools of calculus at your disposal, you are well equipped to start tackling them. I hope that you carry with you the curiosity, analytical skills, and insights that you've developed this semester into your own careers, and that they serve you well. Good luck as you finish up this semester, and beyond.